and now is the time that we will start to present. Okay, so ladies and gentlemen, I had presented last time on skeletal implementations. Skeletal implementations provide a way of getting some of the benefits of multiple inheritance, but in a safe fashion. But I noted that in many cases, what we're seeking, I don't know if I made this connection explicit, but I will now if I didn't. In using multiple inheritance, whether we're inherited from one class or multiple classes, a lot of the traditional desire for multiple inheritance has been the fact that we'd like to be able to draw functionality from many sources. We'd like to be able to have our code base that reuses mechanisms that are outlined in many particular classes, many particular sources, and weave them into our own class. We'd like to be able to achieve reuse of that tested implementation from other classes. And with multiple subclassing, we run into a set of issues. We can, because of issues with let's call it substitution principle, we can run into cases where we can get, and this is with subclassing in general, where because we have polymorphism, we need to be careful that the subclasses have promises that are consistent with those of the superclasses. We can have subclass issues even with just one superclass, where a change to the subclass breaks the superclass, or where a change to the superclass breaks the subclass. But with multiple inheritance, we saw additional problems. We saw this diamond problem, where you get this confusing situation where you have a student employee, and then you have a student superclass, an employee superclass, and they share a common person superclass. And in general, with type hierarchies, it can get very confusing about what are the common ones, and you can get confusions very easily. Also, you can get questions like get designation might be defined as both student and employee, and the question is which you end up using. So the encounter of object-oriented programming, class-based abstraction, with multiple inheritance has not been a very comfortable one. And researchers at one point realized that what they'd like to have might be a little bit different from multiple inheritance. It's this capacity to mix in functionality from multiple sources in a more flexible way. Maybe it doesn't always have to come along with polymorphism, but we'd like to be able to weave things together. And we saw a little bit about how we could get bits of flavor of that within the context of skeletal implementations. But today I'm going to be presenting Scala traits as a way of achieving Mixin functionality. Okay. So traits in Scala have several roles to play. They basically generalize the capability of interfaces as used in Scala. They can provide some implementation, but in some ways sometimes they serve as kind of interfaces. And they provide a means of implementation reuse. And as we'll see, it's a very flexible means, a means that can be applied at point of allocation, not merely in statically declaring a class, while sidestepping complexities associated with multiple inheritance. Okay? So you can mix in traits for a class, or when you allocate a particular object, I could say, hey, give me an object that's from this class with this mix-in, with that mix-in, where those mix-ins are traits. Okay? Now, traits can inherit from classes, but they can actually do so in a way that allows for chaining of implementation. Okay? And they allow for instead of replacing the implementation and all other things, it can actually link in with other traits. Okay. So we're going to see a bunch of examples of this in coming minutes. What I've talked about is awfully abstract. But I'd like to introduce, before we dive into it, just a few other pointers here. Here, classes that use traits often inherit from one other distinguished superclass, but then they use this with construct to mix in a trait. So here, you'll notice I'm saying foo, this instance foo, is an instance of class capital foo, but it's mixed in with a trait, okay? So this trait is mixed into this class foo, and its functionality will supplement what's available on foo. It might even fill in missing elements of foo. So maybe it has a certain type of logging associated with it that fills in for the logging of foo. Or maybe it delegates, it does some logging and then will delegate other logging to be done with foo. So the idea is we have this with, okay? And the way to read this is you read, this is a foo with trait, rather than it's a new foo with trait. It's a new foo with trait, okay? And with class, so this is for individual instances. With class, we'll use extend. We'll say class C extends D with A, B, C as traits, okay? And there again, the way to read it is to say class C extends D with A, with B, with C. So it extends the whole package of them, okay? Here we'll see with this keyword we can sort of layer it atop something that have some commonalities in the sense that they inherit from some common superclasses. Okay. Now all Java interfaces in Scala, we can use any Java interface as a trait. But traits can also provide implementation beyond what you can't provide in an interface, okay? So we'll have things like this. Class, my experiment, extends, and again, the way to read this is it extends what? It extends simulation experiment with visualizer with run logger. That's all one thing that it extends. It extends the simulation experiment with the visualizer mixed in and the run logger mixed in. That's a class, and my experiment is going to extend that, okay? Or my logger is going to extend logger with timestamp with truncated with clonable. That's going to be one thing that it extends, okay? And these latter things, so simulation experiment, that's a class with visualizer and run logger traits. Logger, class, timestamp, truncated, clonable, trait, okay? And we can do similar things with when we allocate the class. So we call that kind of the compound class, this simulation experiment with visualizer, with run logger, or logger with timestamp, with truncated, with clonable. That's the compound class, okay? And critically, and I'd ask you to make a note of this, because the chickens will come home to roost in a few minutes, okay? Probably 15 minutes or so. The order does matter. The order of the traits matters. The one that's at the end will be the one that starts first, and it can delegate to the next, and delegate to the next, and delegate to the next. So changing the order, they do not commute. Changing the order changes the functionality.
Wait, did you say from right to left?
From right to left.
Okay.
Yeah. So it's from right to left. So run logger will be the first. It delegates to visualizer. It delegates to experiment, and so on. Okay. Yeah. Okay. Right. with traits, we often use abstract methods. And one way we can indicate that they're abstract essentially is to not, just like in Java, when we have an interface, we don't have to say abstract method foo, abstract bar. We just put in foo as a method. And it's in an interface, so it needs to be filled in. So it is here, that if you don't fill in a method in a trait, it's viewed as abstract. You can also put abstract in, okay? Now, you can also in trait, however, in contrast to interfaces, you can provide an implementation, okay? And often those implementations then call the abstract methods, okay? We will see this functionality used in some of the examples. Okay. So let's take a look at some traits. Enough sort of high-level discussion. So here's an example of a trait, and this, like a number of the other examples, are drawn from some very good discussion by Kate Horstman in his book Scala for the Impatient. Okay. He also wrote a book, Java 8 for the Very Impatient, which is thinner. Okay, which you might want to check out. Okay, Scala for the Impatient has actually this is a variant on it. I think I didn't use it exactly. So here's a trait, and it's a logger trait. And here we define a set of methods that are used by this logger trait. Now, one of them is abstract. It's not filled in. There's no implementation given. So that is going to need to be filled in by any use of this trait. Okay? We'll see how that plays out. You notice the other methods call off to that abstract method. So info, for example, calls log, warn. There. I'm not happy with that. Let me. So this would be warning, and this would be severe. Okay. Okay. So here they call off to this, and you could think of this a little bit like an interface in the sense this isn't filled in, but it provides some implementation for some methods. Okay, now, how do we use that logger? Well, one example is we use it, with traits, we use it with typically. So here we have a class savings account. This extends account with logger, so it extends account with logger, okay? And you'll notice what's going on here, that we have a class here, which then has some code, and we're calling off to severe, for example, and that's going to be calling this method in the logger. But you'll notice that there's something missing. What's missing here? What's not complete? So this is a class. It extends the account. It extends account with logger. But what still needs to be filled in? So we can call off to severe here. But what still needs to be filled in?
The log method.
Yeah, the log method is not yet set. So savings account is still, in fact, an abstract class from that perspective. So what we can do is we can say, okay, when we allocate an instance of savings account, we can weave in which logger we want to use. So here we say this account is a new savings account with console logger. Okay, so we have console logger being woven into savings account in a way that defines log. And in fact, I show an example implementation of console logger here. Console logger extends logger, so it implements the things in logger, it inherits from the things in logger, but it also defines the log message. And by virtue of the fact that it defines the log message, that's what allows us to weave it into a savings account in a way that fills in what? Fills in log, right? It fills in the missing log. Logger here is the supertype of console logger, right? In fact, it is the supertype. It's also this is console logger is inheriting from it, and console logger is providing an implementation of log. And here, when we instantiate savings account, we are weaving in console logger into savings account. Savings account doesn't have an implementation for log by itself, right? This inherits from logger, which still needs log filled in. So savings account by itself doesn't have a log. So in normal Java, we wouldn't be able to instantiate it. But here we can instantiate it because for this line here, new savings account with console logger, where's the log coming from?
Console logger.
Yeah, it's coming from console logger, because console logger has the requisite log. So we've woven in console logger's implementation of log into savings account at the time of allocating the object to create a console log savings account. Alternatively, separately, we could have a new savings account with file logger, and file logger would provide a log message that logs to a file, and it would fill in the requisite missing piece, the log associated with savings account. You see what's going on here? So here we are using this trait. We have a missing piece of it that can be woven in by another trait, here console logger or file logger, to fill in the missing piece, and we basically piece them together. That's the missing piece of the puzzle. That's the log, we put it in, and now we have a complete class that we can use in our object. And we can choose at runtime which one we want to weave into it. Do you see that? We can choose at runtime. Do we want to use savings account with a console log or savings account with a file logger? That's something we can choose here at the point of allocation. We're putting the pieces together at point of allocation. Do you understand that example? Okay. Who has a question about that? Okay. So I'll go on to another example. I may get into issues with self-types, which have an interesting link to several features within the language space. Now, before some more examples, I want to emphasize one or two things here. If a trait extends a class C and is being requested as a trait for class A, there's some rules here. Okay, so if a trait extends class C and is being requested as a trait for weaving in with class A, there's two cases which are okay. Okay, if the class into which the trait is being mixed has no explicit superclass, that's fine. The trait has a superclass, A doesn't have a superclass. We're saying we want to mix in this trait with A, that's fine. Now, another case that's fine is if this superclass C is already present of a superclass of the thing into which we're mixing, then, and that's also the superclass of the trait, then that's also fine, and C is only built once, okay? What you can't do is mix in to a class whose superclass does not include C, okay? This is a bit of a subtle point, but it basically has to do with the fact that we can weave into things that have common superclasses. So check this out here. So we have savings account, for example, extending account with logger here. So it needs a logger, and console logger superclasses also logger, also inherits from this logger trait. So both of these, console logger and savings logger, inherit from this logger trait. Do you see that? And as a result, we can weave in console logger into savings account. It will be able to weave it in because it knows to expect a logger. So here we're weaving in to something where C is already present of a superclass of the thing being woven into. What we're weaving it into is savings account, and logger is already a superclass of that. Okay, let's look at some more examples here. Okay, so here's a slightly different case. So here we are going to have a trait log, which is going to be different in the sense it provides an empty implementation. Okay, and savings account here is going to extend account with logged, and it's just going to call off to logged. Now here we can have a console logger that defines log in a different way. Okay, and here we can create a new savings account with console logger, and in this case, the logger associated with console logger will be fired, and it is going to be the one that is used rather than this logged implementation here. It's because we've woven in console logger and it's provided a concrete implementation. That one is the one that will be called first, and in this case, this other one is not going to be called by it, and so it's not called. Okay, this empty action one. And similarly, we could create one that's a file logger like this with savings account, and it would. So this is a different way of implementing that earlier functionality that actually provides an empty implementation here rather than an implementation that is abstract. Okay? Now, I'm showing this example partly in hopes that it will prepare for the next step. So in traits, I haven't shown it yet in these slides we've seen, but in traits, we can use this syntax and call super dot a certain method name, okay? And basically what it does is it calls the next implementation down in the chain of things mixed in, okay? And what's the next one depends on the order. And it starts with processing the last one, and so it basically will, if this is, partway through the list, it will go to the next one earlier in the list. It starts with the last, goes to next to last, etc. Okay, and there can be more. There's a good reference on this in Scala references. So let's check this out. So here you'll notice that building on the last example, we have a logger where we have an empty implementation. Okay, it does nothing, but it's not abstract. And then we have info, warn, and severe. And once again, these need to be corrected. Oh, final announcement. Thanks to Andrew, I updated the Scala code. There was a bug associated with processing of arguments that occurred in a very particular case. And Andrew caught it, and I updated the Scala code for the assignment. Okay. That's in problem 3. 3 or
which particular part of
it was for the Scala code for the Game of Life.
Yeah, I had like a bug somewhere. I'm curious.
Which function?
It was in the one that parsed the arguments, command line arguments. Yeah. Okay. So back to the salt mines. So here, ladies and gentlemen, we have a trait logger, and this trait logger is like the last one we saw. It doesn't do anything. You call it, it doesn't have any action. And we have info, warn, and severe that delegate to that log message. Okay, that log. Now here we're going to have a trait console logger, which is going to provide a log, an implementation for log, but it's going to do it with a twist. Okay. And ladies and gentlemen, now let's do the twist. Okay. So here, this implementation is going to call off to super.log. Okay. So what's going on there? What's going on with the twist? Okay, the salt mines are wearing on people. What's going on with the call to super.log? What's this calling? Yeah. It's not necessarily call. It could call an empty method. It's going to call the log on the next trait down. Okay. So whatever the next trait down is, it could be empty. It might not be. Okay, so here we have a class savings account. We call off to Spirit, and you notice that the savings account includes this trait as something, as a trait defined with, so it extends account with logger. And then we could use this account and we could say, okay, we have a new instance of savings account with console logger with file logger. Okay. So suppose I call the log message on account here. Whose log is going to be called? Sorry?
First to the console logger, and then the console logger log message will call the file logger.
Okay, almost, but it turns out by an ugly fact that ruined a beautiful theory, it turns out it's the last one that's called first. Okay? Last in, first out. Well, not quite, but file logger's log is going to be called first. It's going to delegate to console logger, and then whose log is going to be called? Who are you going to call? I got to keep it live, you know? So what's that? Savings account, yeah. So savings account is going to be called.
What if savings account doesn't have log?
Sorry?
What if savings account doesn't have a log method?
Then it's going to cause problems because it is going to not be able to cause that, and you'll get an error message at time of compilation because you do not have a valid implementation for log associated with savings account. So I'm virtually certain that's going to basically give a compilation error associated with that. So this is why here we are providing an empty implementation. So it just does nothing. So here, ladies and gentlemen, we have a weaving together, yes, but it's not merely, I want to distinguish this from the already notable ways in which we had a weaving together here. I mean, here, when we allocated a new savings account with console logger, there was a real sense of mix-in here. We were mixing together at that point of implementation the logger functionality with console logger, and we were putting it together with the implementation of savings account. We snapped them together just like two puzzle pieces, right? And we got out a complete implementation for that. So there we kind of wove them in. We wove in console logger in a flexible way into this functionality. But here we're doing something a little bit richer than that yet. We're actually weaving together several implementations, and we're having them interact. So file logger can hand something off to console logger, can hand something off to savings account. And what do you think this is going to do? Well, it's not going to bust your ghosts, but what is it going to do? Well, when I call log on a count, what's going to happen? Where is it going to be logged? Console and file, both, right? File and console, because the log associated with file logger is going to be called. It's going to do its job. It's going to do its thing, which is presumably pointing out to a file, right? And then it's going to call off to console logger, which is going to do its thing, and it's going to call off to the savings account. True or not?
Is it going to call regardless if you call super.log or?
So no, if you left out super.log, it would not in fact call. So that's why in this previous, so if, sorry, I'm not being clear enough in my explanation. If this console logger did not call super.log, the call chain, when you call log, would end at console logger, because it wouldn't call on to the log associated with the savings account. It wouldn't call on anymore. So it's an elective part of this that they are chained together. And in fact, this is what happened there. When you weaved in console logger, that's why I said if you called log on account here, it would call this log to print it out, but it in fact would never reach this point. Do you see what I'm saying?
So file logger also has
Yes.
super.log.
Yes. I didn't want to try to fit it into this screen, but maybe I could have put it here above console logger. So it would be comparable def log. It would print it out to a file, and it would call off to super.log. So here, where do we see super in Java now?
Constructors.
Yeah, we see it in constructors. So we'll have one constructor, delegate to the next, delegate to the next. And by the way, there can be serious issues if you don't delegate, because the super class won't be properly constructed. May not be properly constructed if you don't delegate to it in your constructor. Does that make sense? Okay. Okay. So, ladies and gentlemen, here we have logging of several sorts, and we're weaving them. We're weaving them together. So let's consider this here. This is a new variant of that. Here we have a right. And I'm just parsing this. Yes, exactly. Okay. So this addresses the Tushita question. Okay. Okay. So, ladies and gentlemen, here we have a logger. And how does this logger differ from the one in the last example? What's different about this logger?
Doesn't have an override.
Yeah, this. Yeah, I heard it. I think two.
Doesn't provide emails.
Exactly. So here, this is abstract. There's no implementation provided for this, whereas previously we did. Now, Tushita expressed a very good question, as is typical for her. She asked, what would happen if this had no implementation, and we called super on it, right? What would happen here? And I'd like to show how this particular example handles it. Okay, so there's going to be a twist with that. But beyond that, we're going to have a console logger here, which is going to extend logger. And you'll notice that this implementation differs from the last one. How does this implementation differ from the one we saw previously? It doesn't call the super log. So console logger is in fact is in fact not here delegating to the next one down the line. Implicitly here, we're kind of assuming that we're only using one logger type, but we're going to have decorators, which are going to decorate. Now, we could, of course, fall back and actually have an implementation of log, in which case this could delegate super.log in console logger. But this is showing a somewhat different feature. So the Tushita question was, what if you had super.log called on something that's abstract? It's not going to work. So this just doesn't call super.log. This is woven in, and you need at least one logger woven in. But then we're going to have a different sort of delegation going on. So we're going to have traits that are decorator traits. Timestamp logger decorator and counting logger decorator, okay? And each of them is basically going to keep track of different sorts of information, and in fact print out that information. So timestamp logger is going to basically take in a log message, and it's going to timestamp it with the current time. And then what's it going to do? It's going to call super.log. It's going to hand off that message. Notice it doesn't print it out. It gets the message read. It puts some information around the message, and then it hands it off to the next thing. Counting logger decorator is going to be counting up the number of logged sort of messages, and it annotates them with the current message count. This is the third log message, so 3: and the name of the message. Okay? Now, what's going to happen here is that we are going to have to, so here's our savings account. It extends account with logger. So what thing do we have to fill in? Would we be able to just say new savings account? Cannot. Cannot. You need an implementation of log. May have heard that from Nobleman in the back. You need an implementation of log, and savings account by itself doesn't have an implementation of log. Ladies and gentlemen, savings account extends account with logger, and the logger has no implementation of log. So we can't allocate savings account. We need at least savings account with a logger, and in this case, it's savings account with console logger. It could be with file logger alternatively. But we're going to be able to weave in these decorators. So this is actually going to be a savings account with console logger, with timestamp logger, with counting logger decorator. So when we end up calling log on that account, what are we going to get? What's going to happen? Who are you going to call? Sorry?
All of them? All of them?
Yeah, it's going to call all of them. And in what order? What's this the first that's going to be called? Counting logger decorator is going to be called. So it's going to, we're going to call it with some message. We're going to log the message connecting to database or something, right? And it's going to label that with a line number, and it's going to call super.log, which is going to pass it on in this case to what? Timestamp logger, which is going to further label it by the time, date and time, and then it's going to call on to what? The console logger, and console logger is in fact going to print it out on the console, and it doesn't call on to anything else. It can't, in fact, because the next thing is abstract, and it would cause a problem. And it's a problem that could be detected at compile time. So here, ladies and gentlemen, we have a different sort of delegation. Here, we're not just putting out the log message to different destinations, file, console, etc. We are in fact decorating, we're adding information in to be logged, and the console logger is the one that finally disposes that by putting it in the appropriate point. And by weaving together different decorators, we could have log messages of different sort associated with our objects, right? So we could have them annotated with different types of information. So here we have, again, a use of this sort of mix-in functionality. We are deciding in a very flexible way on a per line of code basis which functionality we want to mix together from different sources. And we don't have to do so in a static class. We could do so at point of allocation, say, hey, mix this, and in a way that allows for this sort of delegation. Okay? There's some additional examples here that I include and that provide sort of variants of this. So the timestamp logger and a short logger, for example, and bear in mind that the order is very important. So if we have timestamp logger, with console logger, with timestamp logger, with short logger, the order may matter in terms of functionality. In this case, one of them truncates it to a certain size, others add a timestamp onto it. Whether you do one first or the other may make a difference in terms of what you see as the output. Okay. Just matching here, we're just about at time. Traits, as we've seen, can contain concrete methods or abstract methods, and the same thing with fields. Okay, so they might have an abstract field, an integer that has to be filled in, and they can be filled in by things woven into this, with this trait. It could fill in an implementation of that. Okay. There's some fascinating issues with variants on this that I don't have time to get into, and some issues with constructors for traits, construction order, etc. Behind the scenes, if you were to use Java P and so on, you could explore the fact when you use these, there's interfaces created that is an accompanying class, and there's some ways in which it gets basically unpacked into Java data structures. So, ladies and gentlemen, mix-ins. Mix-ins provide a way of easily drawing on the functionality of many sources, doing so in a way that avoids the burdens associated with multiple inheritance and many of the risks associated with classic subclassing when used to try to achieve functionality without care. Mix-ins provide us this way at the time of allocation of weaving together multiple types of interacting functionality, of weaving it together in a way that it fills in the missing pieces, whether it's fields or whether it's methods. We can weave these things together and have them interact in a fulsome way while at the same time achieving great flexibility. Scala traits provide one way of achieving mix-ins, one way of many that's been explored within the language space. They're a very attractive, in fact, widespread mechanism in the Scala libraries. So there's much Scala functionality in the libraries that are provided with traits as their basic implementation. At the same time, they can leverage aspects of interfaces. So that's all for today. I'm going to be working myself some on some of those marking issues and working towards getting you those marks by Saturday. We also are going to have to schedule that review, so please be sure to vote on review times if you're planning to go. Okay? Thank you very much.
I received the time schedule for p-hack meeting. It's at the Central Time Regina, so which time?
Same.
Same. Here, the
Uh,
Saffron time. Okay.
Same
In
time.
case last time I missed the 1 hour.
Yeah.
So and I send you the model.
Oh, okay. Yeah,
Okay.
that's good. That's good. I'll look forward to going through that. Okay.
Okay, sure.
Okay.
Thanks.
Okay. Great. Thank you.